Good afternoon, everybody. Thank you for joining today for this webinar on differential scanning calorimetry. We're just going to hold on this screen for a few more minutes and let some other people join. But yeah, I'll talk to you in a few minutes. Okay, good afternoon, everybody again. I think we'll wait another minute or so, but we are ready to start. Hopefully you can see my screen sharing with the title page of the webinar that we'll get into in a sec. Okay, so good afternoon, everybody. Thanks again for joining today for our Sigma-HSE webinar. Today on the topic we are talking about is differential scanning calorimetry for chemical process evaluation. So it's going to be myself and my colleague Luke that are taking the webinar today. So I'm the laboratory manager for our chemical process evaluation laboratory here, and Luke is one of our technicians in the lab. So yeah, we're just going to discuss this particular instrument and how we use it for measuring different parameters and doing our assessments for our clients.
So yeah, just a little overview then of this session. We'll be exploring the use of the differential scanning calorimeter and how we can apply various thermal stability data and thermophysical properties for chemical process evaluation. So you can see we split this into 4 sections for today, just briefly outlining what is differential scanning calorimetry, how it works, when to use it, and then also look more in depth at how we can assess reactive systems and the thermal stability of your raw materials or reaction mixtures, and understanding how this factor regards reactive hazards and the various testing methods. We'll then look to understand a bit more about the thermophysical properties that we can get from certain types of DSE testing, before we'll try and tie this all together for you about how this can be applied in a chemical process evaluation.
Yeah, as Luke said, hopefully covering those kind of topics that we gave there in the overview that we're going to go through 4 sections. We'll have covered some new ground, hopefully, and that we'll learn a bit more about, firstly, DSE, the equipment itself and its varied application and different uses, the different testing methods that we can employ to look at certain material characteristics, and yeah, the kind of material properties that can be studied using this instrument. And then finally, trying to tie it back to what we're doing here at Sigma-HSE, how it all relates back to our clients' processes, or indeed your processes here on this call. So really, we need to demonstrate it is our job to understand how to use the equipment and to select the appropriate testing methods, and additionally how to make the best use of the data to apply to your processes in industry to ensure safe process, scale up and continuity, really. So Luke, if you'd like to take the next slide, we'll jump into what we do here at Sigma.
Yeah, so just a brief overview on the testing capabilities we have here at Sigma. Obviously, this presentation focuses on the differential scanning calorimeter, but really this is just a small part of the chemical reaction hazard testing that we can offer. We also have reaction calorimetry and adiabatic testing, which they're all essential for designing and fully understanding your process. So in addition to this, we have more bespoke thermal stability testing regarding some UN testing, UN test 10.4, self-heating substances, which is essential to ensure safe compliance with transport regs. We can then also simulate realistic drying scenarios from your process, talking about sort of thin film residues and to even bulk materials under airflow. And this will just help us to assess decomposition risk in these scenarios. Then moving on then, so obviously if you have a process and the end product is a powder, as a solid, then we also have a wide range of powder, dust, fire and explosion tests to help evaluate whether your solid materials are combustible or not. And if they are, how sensitive and how severe can they be? Similarly, we can also determine these properties for gases and vapors, and that's in the form of flammability limits, flash points or ignition temperatures. And finally, we can also test the electrostatic properties. This is obviously especially critical for, if your material has a very low ignition energy, but also, we can not only test your material, but the materials of construction, and we can test for charge accumulation, resistivity and discharge risk. And all of this can help support a proper and safe process design.
Yeah, thanks. And additional to that at Sigma, as our laboratory facilities, we also have a consultancy team of engineers that assist our clients with a variety of different process safety assessments that can be selected for the specific requirements of the client. I need to change the slide, one sec. So I'm aware that some of these assessments or regulations we're going to cover in this webinar are European and UK based, and we have some international people on the call, so apologies for that, but there are applicable local regulations in place of the ones we're discussing that cover similar topics. But some of the assessments that our teams can assist with look to firstly identify potential hazards in systems and processes, such as hazard, desir, PHAs, and so on, while others can look at mitigations or the integration of mitigations and controls and proactive methodologies that should be, each of these assessments should be chosen and applied based on the niche requirements of a certain process under assessment, or indeed the phase of construction or planning for a new facility or so on. So quite often these assessments can either result in a need for our CRH testing or other process safety testing, or indeed will use already available testing data, such as DSC data, which we're going to go through here today, to make grounded and justifiable informed decisions on process safety assessments and controls. So to understand next how such a small and widely used laboratory instrument can really help with process scale, bulk scale assessments in industry, Luke is going to talk next about some of the basic principles of the DSC.
Yeah, thank you, Ollie. So obviously, before we get into it, it's important to understand what DSC is. And as the name hints to, differential scanning calorimetry measures the thermal behavior of materials by measuring the difference in heat flow. And that is the difference between a reference crucible and a crucible containing the sample. And this is usually as a function of temperature, but can also be as a function of time. So usually this reference crucible is empty. But if we imagine we have two empty crucibles, same weight, same material, we would expect to see a constant differential heat flow. So 0 milliwatts, because there's essentially no difference in the heat flow between these two crucibles. And we can see in the diagram in the slide here, with the sample and reference crucibles, they have independent temperature sensors and independent heaters. So once we then add the sample to this situation, we can assume that all the differential heat flow is associated with the sample. So endothermic events like the first peak, which trends downwards in the graph on this slide, the endothermic events occur when the sample absorbs heat from the surroundings. So in a ramp test, this is when the energy supplied to the sample crucible is greater than that supplied to the reference crucible. So then when we subtract this heat flow from the reference heat flow, we then get a negative value. So this is shown by the negative heat flow in the graph. And then the opposite is true for exothermic behavior, where heat is then released by the sample, meaning less energy is supplied to the sample crucible than the reference crucible. And again, when we subtract this negative heat flow value from the reference crucible heat flow value, we'll then get a positive value. So in this graph, we can see it has a exo on the y-axis to show that exothermic peaks are positive. So in some methods, it's necessary to use a reference material, and this reference material should have known thermal properties and will be chemically inert over the temperature range of interest. We'll discuss a couple of these methods later on in the presentation, but overall, the DSC is a simple but extremely sensitive instrument and provides resolution at the milliwatt scale.
Yeah, thanks, Luke. I mean, I've heard of a sort of affiliated method sometimes with DSC being TGA. Does that work in a different manner?
Yes, so TGA, or thermogravimetric analysis, measures a mass loss from a sample over a temperature range. So this can include measurements of loss of water, so moisture percentage, which can be important for quality control, but it can also sort of measure the amount of gas produced in decompositions. So whilst it doesn't directly replace DSC, it's usually used in conjunction with it to provide sort of further insight into decompositions, because DSC for thermal stability applications will typically use high pressure seal crucibles so that we can more accurately determine enthalpy, so that no heat is removed from the system, as is the case in sort of thermogravimetric analysis.
Great, thank you. And to sort of add to that background on what is DSC in part one, we'll go through when exactly we might consider to use DSC in a new process development timeline. And as we'll go through later on in this webinar, due to its generally quick testing methodologies and very small sample requirements, the DSE really is a very useful piece of equipment to use at early stage development or R&D of new processes or new syntheses to give very clear indicative information regarding your raw materials, intermediates, products, or reaction mixtures in some cases, and can help to make useful choices early on at these early stages. So we have that sort of represented graphically on the right-hand side where we have a process moving from a particular target product that we want to synthesize for some reason, whether there's market forces or so on. We're starting to look at how we might synthesize that compound, starting to look at thermal screening, which is what we mean by DSE in this case, which can really help either show the feasibility of a certain process or to rule out certain choices of different materials and so on. So that's what we talk about early stage testing. But additional to that, we can also start to use DSE to assess maybe we're considering a pre-existing process and we're looking to swap in different raw material feeds or make changes to an existing synthesis. Then using DSE in that case can also give quick confirmation on whether those material swaps or changes are safe to use in place of previously assessed materials. And then finally, in sort of later stages development, moving from this sort of pilot plant scale to production, using DSE for measuring thermophysical properties, which we're going to cover here later, can really help inform on reactor specifications and builds, design, and process optimization for taking syntheses to bulk scale for production.
Okay, so moving on to part two, we're going to look more specifically about how to assess the thermal stability of materials, but also how you can use DSE to characterize your desired reaction. So from a chemical reaction hazard standpoint, the data we are most interested in is the exothermic behavior of your material. And this is because the generation of heat from your desired or even undesired reactions can trigger decompositions that generate gas. But also the heat itself can increase the vapor pressure inside your vessel. So it's these unknown exothermic events which pose the most significant risk to your process. And so the useful data we can extract from typical DSE scans includes the onset and offset of any exothermic events, also the enthalpies. So this data can help us to screen hazardous materials from a whole range of materials and help us narrow down and streamline, identify potential chemical reaction hazards, which can then help support in the determination of worst case scenarios. And these worst case scenarios are needed for further adiabatic testing and even further down the line for vent sizing requirements for emergency relief systems. So this initial data allows us to provide a basis of safety built on a solid foundation of experimental data. Furthermore, the data enables us to determine process parameters and influences process design by providing enthalpic data that can be used to calculate and estimate cooling and heating requirements of your system. Again, it's talking about, is this going to be feasible? This information, these sort of thermal scans are typically obtained using high pressure crucibles with the thermal scan from ambient to 400 degrees Celsius at rates of 5 to 10 degrees a minute. So at Sigma-HSE, we are ISO 17025 accredited to ASTM standard E537. And this is the determination of thermal stability of chemicals by DSE. Similarly, we also are in the process of getting accredited to ASTM E1260, which is another standard, which is the heat of reaction of thermally reactive materials. Moving on from your sort of standard thermal stability scans, this also extends to things like resins, where we can employ similar methods, and we can determine the degree of curing by ratioing the exothermic energy between uncured, partially cured, fully cured resins. So again, some really useful variability. Other methods can also be used, and just touch on in this slide, for transport and storage materials, we can determine things like SADT, self-accelerating decomposition temperature, time to maximum rate, and TD24 of materials, which I think Ollie is going to speak more about on the next slide.
Yeah, as Luke just highlighted there are certain ways of operating the DSE and the following analysis of the resulting data that can really be tailored towards specific applications or uses of the material in question. For example, thermal stability studies specifically tailored for meeting transport regulations. We can firstly screen samples with a constant heat ramp test, and then design an array of DSC tests to estimate SADT values for materials if required. So SADT, that is self-accelerating decomposition temperature. So that is an exothermic decomposition reaction that we don't want to occur. And we especially don't want that to occur on bulk scale during transport on a tanker or a ship or so on. So materials that have an SADT below designated thresholds will require additional controls to be put in place for transportation, such as temperature controls or cooled shipments and so on. So really it is a key factor to consider as we were talking about thinking and using DSE at early stage process design, not just how we're going to produce this target material at our production site, but how we're going to ship it to our clients who are paying for the goods at the end. So the transport considerations really is a key factor to consider when scaling up production of a new product for this reason. So using that initial thermal screening ramp that we can do following ASTM E537 that Luke mentioned in the last slide, if we see evidence of an exotherm that is moderately or extremely strong in terms of its enthalpy, and it is present below 160 degrees Celsius in the DSE, we would it is signposted that further testing should be done to elucidate the SADT value of the material and to further check whether temperature controls are required. This can be done by further DSC tests, isothermal tests, which can study the kinetics of the exothermic reaction and can be used to quite confidently estimate and calculate SADT values for the packaged articles. This can be a much quicker and cost-effective route to understanding SADT of materials rather than going straight into the full packaged article tests or Dewar tests required to meet the transport regulations. The same is true of not just self-heating properties, but also explosive properties for transport regulations, where DSE again provides a good small-scale test to rule out, hopefully, this potential for explosivity. But again, if certain thresholds are met, it will signpost to further testing required. The same kind of principle can be applied to isothermal kinetic evaluations of either desired reactions or undesired decomposition reactions to inform on TMR, time to maximum rate, and TD24 of exothermic reactions, which can be used for internal designs and process assessments rather than just for transport. So over and above the raw numerical outputs from DSC scans, with good knowledge of the test material and the sample, certain conclusions can also be drawn from the shape of the peaks. So not just the position of the peaks, but how sharp they are. If they have shoulders to either side, we can really read into that and start to point to different nth order reactions, self or maybe auto-catalyzed reactions may be present within the system. Additionally, active compounds that exhibit exothermic behavior can be substantially affected by the choice of solvents in which they're dissolved. So it's commonly considered that inert solvents, not themselves being with a potential for decomposition, will have little effect on the thermal stability characteristics of the mixture, but onset temperature of decompositions and their exothermic enthalpies have been evidenced to be affected significantly by the choice of different solvents. So we've referenced below here a very good paper from a team at Syngenta who highlighted this phenomenon they found. So that's something else to really consider, that not just thinking as a solvent in a reaction mixture as a innocent bystander in a exothermic runaway reaction, but also potentially can really affect the behavior of the system when the dissolved material is actually decomposing or behaving exothermically. So we've discussed and focused here now in this section a lot on exothermic behavior. So Luke, do you want to tell us about some endothermic analysis that we can also perform using our DSC?
Yeah, thank you, Ollie. So moving away then from the thermal stability and the data associated with exothermic events, we can now focus on the analysis of the endothermic data that we see in the spectra and how we can use it to assist in chemical process evaluation. So we can study the typical endothermic phase changes associated with melting and boiling temperatures of a material. Understanding the enthalpy and onset temperatures of these events can be essential for just the handling of your material, but it can also help you to optimize and determine your process parameters. Think this can be especially important when your process has reflux steps or distillation steps. Having accurate data is really important. But then moving on to sort of the thermal characteristics of your material, so specific heat capacity measurements, not just of your raw materials, but your mixtures are necessary not only to understand the energy requirements for heating and cooling in your system, but they're also required to accurately calculate vent sizes for emergency release systems later down the line. And similarly to sort of the specific heat capacity we have in the case of polymeric and amorphous materials, knowing the onset and magnitude of glass transitions is also really important because they can directly affect the specific heat capacity, but also material properties which may make a polymer easier to handle. So again, it can help optimize these processes, determine these process parameters. Furthermore, you can compare these glass transition values with literature, and this can be used to help for quality control purposes, but also optimization of sintering or molding processes. So similarly, DSC can also provide insight into purity and crystallinity of your material, again, which is useful from a quality perspective. And you can imagine how essential this would be, especially in pharmaceutical industries. So you can see on this slide the different types of pans that we can use for the DSC. Previously, we talked about the high pressure crucibles that we use for thermal stability testing, and you can see that here on the right hand side. But for these thermophysical methods, it's required to use a material which is more thermally responsive. These sort of transitions are much more discrete compared to something which is quite violently exothermic, for example. So we need a material which is lighter and more thermally responsive. So instead of the incloi we use in the high pressure tests, we use aluminium. So you can see we have the lid on the far left, and then we have 30 and 120 microliter volume crucibles.
So I'm just thinking, Luke, we specifically for sort of reactor design and vent sizing for emergency relief systems, specific heat capacity and boiling points of mixtures are, as we'll touch on a little bit later, are really sort of critical things to consider in those cases. And why do we think it's important for reaction mixtures specifically to be tested for these parameters when we can typically quite often find CP or boiling points of, say, the major solvents from literature or SDS?
Yes, it's a good point and well worth the consideration. So it also touches on the point you made earlier about how, you know, different solvents can stabilize the intermediates for different decomposition pathways. Even from a basic chemistry standpoint, we know that salt solutions in water can adjust boiling points and specific heat capacity. So when you're designing a process, you need parameters that are as accurate as possible and as representative as possible of your process. So as you know, specific heat capacity is such a key component, especially for latter studies like for vent sizing, and even adiabatic test methods. It's crucial to have confidence in these values and be as representative as possible.
Great, thanks. And like I say, we'll go into a little more detail on some of the methods, because there are lots of methods to choose from for DSC testing, but specifically to look at some of the thermophysical properties that we've outlined here in this talk. When starting to try and look at characterizing discrete thermophysical properties, then really understanding the test material in question and choosing that correct, appropriate testing method is critical. So the different types of consumables that Luke showed on the previous slide really come into play here. Key of which really is boiling point determination. Obviously, of liquids are best characterized with aluminium or some other material, lightweight crucibles with hermetically sealed lids, with a very small 50 micrometer pinhole in the lid. And we've got a sort of a demonstration here of two DSC plots of the same sample tested for boiling point, but using different hole sizes in the lids. So we have the recommended 50 micrometer hole on the right hand side, and then a larger 0.6 millimeter pinhole. So only a 10 or 12 times greater diameter pinhole, but the difference in the measured data is significant and easy to see even to the untrained eye. The larger hole pans suffer from very early region vaporization of the sample. In effect, the hole is too big and it can't contain the vaporization within the headspace of the pan. So we have early endothermic events and we have multiple peaks, it seems, for a pure compound. So as it vaporizes in low temperature regions, we then have an effect called purging, which results in this messy spectra. And additionally, the quantification of the heat of vaporizations, which are recorded here, will not be accurate because we've had that loss of mass through vaporization and loss through the pinhole at early temperature regions, that our calculation of enthalpy will not at all be accurate. And it's also downshifted to lower temperatures, these endothermic peaks, where on the right hand side we see a very nice, sharp, clean vaporization peak at roughly 240 degrees. The other peaks are occurring from 100 to 230. So it's a clear demonstration of choosing the correct sort of consumable to do this kind of an analysis. For some of the other parameters we've discussed, such as melting point of solids or glass transitions of amorphous materials, evaluations require typically less controlled choice of consumables, as no vaporization or decomposition should occur prior to the regions of interest. So if we think a TGE or a melting point is going to occur at, say, 200, we don't want any vaporization or gassy decompositions or so on to occur at less than 200 degrees, because that will, again, invalidate the results. So because of this, we can use open pans, inert headspace if required, if oxidation is a factor, and sealed crucibles. They can all be used with good results, but it's again understanding your testing material, but also your materials that the consumables are made out of. So despite DSC as a whole, this being a differential technique of the sample crucible measured against a blank or a reference empty crucible, wherever possible, the use of a lower mass crucible can result in more sensitive measurement. On the right hand side, yeah, we've again, there is lots of different methods that can use the DSC equipment. We've just highlighted some of them that we use typically. Glass transition, again, with low weight aluminium crucibles, typically determines onset and step height. We're citing an ISO method here, and specific heat capacity. Again, that is a really crucial, critical factor in a lot of cases. And we can determine that with these fast heating rates of 20 degree a minute. And there's different methods to use for that. So we've referenced a lot of ASTM methods, especially in the previous section 2 with exothermic activities. But you may have seen here in this section 3 for thermophysical events, we've cited more ISO methods. So typically, a lot of the ISO methods for DSC characterization seem to have been focused on sort of polymer systems and organic materials, oils, lubricants, and so on, while the ASTM methods we use for decomposition energies that Luke was talking about give much broader guidance for the analysis of a wider range of materials, which really suits our motive here at Sigma of chemical process evaluation and process safety.
That's great. So, Ollie, just a quick question. I'm just wondering if you can elaborate on the shape of the 50 micrometer pinhole graph and why we integrate the peak in that way.
Oh yeah, so just quickly, it's like we've gone through, it's a much sharper and cleaner peak on the smaller 50 micron pinhole size, which is what we're trying to achieve. But we can see a relatively smooth baseline response up to the sharp endothermic boiling point, following which we can see an increase in the heat flow, which would point to a potential endothermic event happening here. So this organic liquid, it is not uncommon for organic liquids to experience decomposition immediately after vaporization or very quickly after. So it's a potential for this sample that it's vaporized very cleanly using the correct pinhole. There is residual vapor in the headspace, which has further been heated and then transitioned into an exothermic decomposition very quickly. So we tend to integrate the heat of vaporization up to the top of this exothermic peak to sort of account for that potential loss in the vaporization energy that we've seen, because the two peaks are overlapping. And also following the ASTM standard, if we were following a thermal stability standard and we had peaks that were overlapping, we could potentially slow down the heating rate to bring these two peaks more discrete from each other. But specifically for the boiling point standard, we shouldn't go any lower than the 5 degree per minute used here. So I think we'll go next on to sort of how we use all of this information and tie it together for chemical process evaluation.
Okay, yeah, cheers for that, Ollie. So now for the last part, as I said, we're going to try and tie everything up and show you how we can combine all of the data we've talked about to give you a full picture of your process purely from using just DSC. So in this slide, we can see how each testable parameter directly applies to process design. So starting off again with the boiling and melting points, which we just covered, these can help directly determine the temperature limits of your process. Moving further down the line, though, it also provides essential data that helps define the criticality class of your reaction and whether tempering of your system is available as a potential safety measure to mitigate any thermal runaway. Moving on, knowing the specific heat capacity of your materials is really essential for not just energy demand calculations, but again, for vent sizing, emergency relief system design, and having an accurate value to put into the software for adiabatic calorimetry methods will give you the most accurate and usable data. Again, more sort of thermal characterization of your material, for especially for polymeric and amorphous materials. Glass transition data can help you to optimize your process parameters, improving the handling of your material. And then last but not least, we have the exothermic data that is obtained from the reactivity and thermal stability studies. Again, this is absolutely vital to determine the potential for reaction runaway and to help identify any potential worst case scenarios. So by obtaining and combining this data from so early on in your process development, you can really streamline the worst cases for further testing, and it will allow you to determine the feasibility of your potential synthetic routes with only milligram quantities. So it's really, really useful, really versatile bit of equipment that you can use to optimize reactions and make informed decisions on further testing routes required for process scale up. And in the long run, it's going to save you a lot of time and a lot of money, especially if you have your own in-house DSC.
Yeah, great summary, and Luke has neatly tied together there all of the sort of the key material properties that we've explored today and their characterization with DSC, and how we might consider each of these in isolation or in conjunction, using them all together to give a full and appropriate chemical process evaluation. So we really apply our DSC data to assess whether there exists a reasonable potential for thermal runaway reactions to occur within a system or process, or not, hopefully it may be, and to screen different possibilities to isolate those worst case scenarios that we may advise to test with other adiabatic test methods and apparatus. These options can be assessed using typical process safety understandings, tools, and thoughts. When exothermic enthalpy and material specific heat capacity is characterized accurately, this can be used to really efficiently calculate the adiabatic temperature rise that a system will experience, for example, in a loss of cooling scenario, and thus the potential then for a decomposition reaction to be triggered that may have been seen and evidenced in those thermal stability DSC early stage scans. We can then also integrate the boiling point analysis that we may have done with DSC into this assessment to assign a criticality class to the intended reaction. So just to walk through that a little bit, we have some plots and graphs at the top, which are typical demonstrations of runaway reactions or their assessments of in process safety and chemical reaction hazards. So we talk about adiabatic temperature rise and calculating that from DSE data. So we see a demonstration of that on the plot on the left, where we may have a desired process within that region 1, where we have a batch of materials and we heat it up to the target process temperature, or TP, in order to commence the reaction and result in our product at the end. So following the desired reaction, we heat it up, the reaction commences for some time following the dotted line, and we cool the batch back down again with our product. If we have a scenario with that light grey region where we lose cooling on the reactor, that reaction, that exothermic reaction, is allowed to self-heat the system, and using the specific heat capacity of that mass of material and the enthalpy of that exothermic reaction, we can calculate that delta T adiabatic. So that is the temperature rise that the system will experience, reaching MTSR, maximum temperature of the synthetic reaction. And then unfortunately in this case, like we say, we may have seen in DSE testing a decomposition reaction at a higher temperature. So in this case, our MTSR overlaps with the exothermic onset of the decomposition, resulting in a secondary reaction and a runaway, which again has its own delta T adiabatic, and a TMR is also cited there that we discussed earlier regarding sort of kinetic assessments and how quickly reactions run away from initiation. And then to the right hand side, we have a figure demonstrating the assignment of different criticality classes. So again, on the left, on the y-axis, we have TP as the process temperature. And then throughout, we have MTSR, again, the maximum temperature of the synthetic reaction, which we've calculated from our DSE exothermic enthalpy and our measured specific heat capacities. We then have MTT, which is the maximum theoretical temperature of the system, which is something normally limited by the boiling point of the major solvent. Again, boiling point is something that we can test and validate by DSE measurements. And then the jaggedy line for TD24 being basically the onset of a secondary decomposition. So you can see that we can fulfill all of the criteria to assign this criticality class, all from data from DSE testing. And these criticality classes clearly assign tasks when developing a new process, whether in the case of no unintended adverse scenarios being present, or class 1, then really not many further controls are needed, and it's a very low risk method to take forward to production. Or whether, if there are certain scenarios that may occur, you've got class 2, 3, 4, what kind of mitigations can be put in place to perform this production safely. Or whether, such as in the case of class 5, whether to reassess the feasibility of taking that reaction any further at all through developmental stages.
So we covered a lot there on the, how useful and versatile the DSE is. You talk about calculating adiabatic temperature rise of your desired reaction. So why would we need any other testing for conducting a chemical process evaluation, Ollie?
Okay, yeah, I mean, we really love using our DSE in it. Love talking about how adaptable it is for certain scenarios, but the small sample size requirement for DSE testing that is a benefit for those early stage studies can come with inherent limitations, such as the difficulty in preparing representative samples of heterogeneous mixtures, potential heat losses during test analysis, and some difficulties in scaling to bulk systems or the use of large safety factors. However, DSE, as we've discussed, really is fantastic for early stage assessments of new materials or processes. Again, due to the small sample size requirement and cost effectiveness. Additionally, if clients are working with toxic or hazardous materials, sometimes it can be very costly or difficult to ship larger amounts of materials to testing laboratories, whereas the amounts required for DSE testing can come under limited or accepted quantities, making shipping easier in some circumstance. So doing this early stage screening and different kind of assessments by DSE really allows the testing program that may require different adiabatic methods and reaction calorimetry later on to be vastly reduced in scale and more targeted on the sort of key scenarios that will ensure safe process development.
Okay, brilliant. So we've talked earlier about the kinds of process assessments that our consultant engineers, or indeed even your process safety professionals, are able to use to assess new and existing processes or facilities. And all of these assessments are built on better foundations using data specifically relating to your used materials and produced products. For example, DSE covers not only flammable atmospheres, but also the potential for exothermic reactions to generate overpressures and thus vessel explosions. We have the hack and dispersion modeling, which can be used to assess the risk to a specific failure mode from a vessel failure due to runaway reactions or venting mitigations. While we have more structured methodology in the form of hazards and HAZOPs to identify and score failure models of a system, all of which often call for testing data to fill gaps in the understanding, to which, as we've covered in this presentation, DSE can be a really cost-effective and versatile solution. Of course, there are other process assessments, and this list is not exhaustive, but just wanted to highlight a couple of the sort of process assessments that we here at Sigma-HSE can, of course, help you with. So, yeah.
Yeah, and that really ties together, again, closing that loop of DSE testing, how we may analyze it for chemical process evaluation, but then also feeding it back into those process assessments that must be done to ensure that we keep compliant with the regulations for processes and transport of these kind of systems. So just on summary today of today's webinar on the differential scanning calorimetry, we've looked at a brief overview of the equipment and the instrument, and really its flexibility and how we can use it in different ways to study certain different parameters or properties. Hopefully also demonstrating how and why DSE is useful to us as a cost-effective screening tool, which really provides really useful experimental data, both hopefully to demonstrate scalability and feasibility of a new process, but also to do it safely. Again, to consider new process considerations, to evaluate hazards and material properties from those early stages, or when reassessing an existing process for any changes. And finally, also how we apply this data into fully evaluating a chemical reactive process. Yeah, and hopefully this kind of approach, starting with early stage development and DSE tests, really streamlines the further required assessments down the line and the testing, providing a cost-effective solution in the long run.
So that's all we have on the differential scanning calorimeter and how we can use it for chemical process evaluation. Hope it was clear for you guys. I've not seen any questions, so that either means you're all really confused or we did a great job. So here we go. So we have one from Suresh. How to calculate time to maximum rate adiabatic values from DSC run data.
Perfect, thanks, Suresh. So these are the kind of kinetic studies that we were pointing to earlier on, and rather than these kind of values coming from a simple heated or a one test solution from DSC, these kinetic studies really require multiple runs, either with different scan rates, an assessment of how the exotherm leads in, where it occurs, and the peak shape, or different isothermal tests to see again about that acceleration of the reaction at different temperatures. So yeah, it's a bit more involved, but we're basically stress testing the material under different circumstances, seeing how it responds, and feeding that into some calculations to infer the kinetics of the reaction, from which we can again calculate time to maximum rate under adiabatic conditions. Thanks, Nick. We've got another one here. I'm not sure I can see. What are the minimum requirements for DSC to be used for safety measurements? So in terms of minimum requirements, where we've talked about difficulty with sampling heterogeneous mixtures, this is really up to an operator judgment of the equipment, to state that they have confidence that they've selected the right kind of material, and for that to be used in an assessment. Likewise, in terms of exothermic onsets, although the DSC, or just continuing that thought, sorry, for the DSC is very sensitive in terms of the measurements it actually takes, because we're measuring such a small sample quantity and it is a non-adiabatic system. We have to report quite large safety factors, which can then mean resulting in further adiabatic testing afterwards. In terms of use of the equipment, potentially, Nick, again, we're handling very small sample amounts, so our internal sort of COSH assessments take that into account of how much material we're handling, and then we're typically using high pressure crucibles, so the material is then contained within the system. There's various different approaches. If we're doing boiling point or melting point open pan assessment on something that's going to vaporize, that can be done under extraction, these kind of things. Yeah. But generally, the very small sample quantity required helps us in this respect. Yeah, thanks, Suresh. Luke, do you want to try this one? Which instrument giving TD24 values, such as DSC or ARC, is better suited for the Stozel criticality class assessment that we were looking at before?
Yeah, so I think ARC is inherently better, being an adiabatic calorimeter. The software will automatically calculate TD24 values. We won't have to try and calculate it ourselves using DSC data. The ARC will use one run, whereas a DSC you'll have to use multiple runs. So without a doubt, it'll be ARC, but the DSC, really, I think that the driving point is that DSC can really help determine the feasibility of your process. If you have it in-house, then you don't have to outsource to try and estimate these sort of TD24 values. And really, DSC, that's what it's useful for. It's a screening method, but we just wanted to highlight how versatile it can be and how it can really streamline the further tests you have to select. So yeah, it's a good question, but arc is definitely better suited for social criticality class determination.
Okay, I think we've got through the questions, but if there is any further questions anyone has, please get in touch with us and we will get back to you via email at a later point. But just again, to thank you all for joining today, and hopefully we've gone through some topics that have been good for DSC analysis for chemical process evaluation. Just a final note to say that we'll be at Chem UK, any of those that have joined from UK or Europe, which is in Birmingham of May this year. So anyone there, come to our stand and we'll have a talk to you about testing. And thank you very much again for joining. Bye.
Thanks, guys.